We have a repeat speaker, presenter here today, and that tells you that he's very experienced, he's very innovative, he's a leader in the field. His name is Dacquay. He works for GeoFease, and he is a native of Canada, but has much international experience in the United States. Now, we love you. We love you. He's got experience in Asia, in Europe, in the United States, and I'm assuming Canada, right? He's a certified Geo Exchange Design instructor, and he has done a lot of work with large systems. Something I didn't know, and I've had a chance to introduce him several times, is that he's an innovator as well. Not only is he reconstructing some of his home up in Winnipeg this summer, just when he's not doing this, but he, in his doctoral work, he engineered studies that pioneered a novel control sequence that enhances ground heat exchange efficiency by adjusting the tint of smart glass windows in buildings. So I'm very pleased, and we're just going to get started right away. Dacquay.
Okay, thanks, John. Well, I'm glad you're the guinea pig to figure out this mic. So we'll just get into it. So today we're going to cover the importance of monitoring geothermal systems. First, we'll go through a little bit of a background, the main problem, overview of monitoring systems, key metrics to monitor, key features for monitoring systems, and then some fun case studies. So to offer the continued education credits, we need to go through some learning objectives. Hopefully, if I do a good enough job, you folks will be able to answer these questions. We'll hopefully learn how to measure a BTU, learn a communication protocol for sending and receiving data, understand the differences between an integrated and fragmented system, and then understand key features for monitoring systems. So a little bit of background. My colleagues and myself come from the consulting world in the ground source heat pump industry, and we get a lot of forensic studies. We're involved in a lot of forensic studies, not the CSI type of forensics, but if a system goes haywire for whatever reason, we try and figure it out and then mitigate that in the future. And through this, we've seen repeated problems through these projects. And the main problem is that a significant number of commercial ground source heat pump systems have encountered issues, and an even greater percentage are not operating at peak efficiency. So why is that? Well, the first underlying problem is that as designers, we're using static models to design dynamic systems. So when you get a commercial ground source heat pump project, you typically start with a building energy model, right? You upload that building to the computer to try and understand the hourly heating and cooling loads for that system. But the problem is, again, even if you're the best energy modeler in the world, it's a static model, and the GeoExchange system is a dynamic system. It's changing every year. So you do your 8760 hourly model, you do your thermal conductivity test, right? You try and understand the thermal properties of the formation. You do your ground heat exchanger sizing with your favorite sizing software, whether that's GleePro, LoopLink, GLD, maybe Transys. You develop your AutoCAD drawings, and away you go. But again, that underlying foundation of your design is that building energy model. That's what you input into your ground heat exchanger sizing software, and it's a static model used for these dynamic systems. And then on top of that, there's a general lack of feedback for engineers with ground source heat pump systems and designs. Second problem is that there's a general lack of communication between the mechanical engineer and the controls contractor during commissioning. I don't know if you folks have been involved with this, but from what we've seen, a mechanical engineer will typically generate some sort of rough sequence of operations, some sort of outline. And then oftentimes the controls contractor is left to fill in the blanks, and that may not be how the original engineer had designed and intended the system to operate. So there's a little bit of miscommunication there, and sometimes the systems aren't operating at peak efficiency because of this. And then lastly, there's insufficient training for building operators. These systems aren't, more complex than conventional systems. They're just a little bit different. And building operators aren't traditionally, they don't traditionally get taught how to operate these types of systems. And if there's not a building manual that's generated from the engineering group for that building operator to learn from, and if there's not user-friendly management tools, that's going to be an issue. And even if you do have a lot of communication with that building operator when you're first commissioning the system, what happens when there's turnover, right? What happens when maybe somebody leaves for whatever reason, and then a new person comes in and then it causes critical knowledge gaps. So what's the solution? Well, in our opinion, it's to use monitoring systems purpose-built not only for engineers and building operators, but also for ground source heat pump systems. So what does that look like? Well, we have our hardware, right, to sense the points that we want to look at. We have the communication interface, data routing, collection, and storage, storing that data, and then the software side, right? How are we analyzing that data, and what are we looking at in terms of the graphical interfaces and understanding that raw data in a palatable form. So for hardware, we have BTU meters are quite common in ground source heat pump systems. A BTU meter is a flow meter and temperature sensors. We also have our power meters for the electrical energy. Since we're electrifying, it's important to understand the kilowatt hour consumption of our equipment. That involves amp clamps, and you need to understand the voltage as well. Amperage and voltage, you get your kilowatt hours. And then in terms of our ground heat exchanger side, we like to look at the water pressure. And on our heat pump side, the refrigerant pressure. So that's the hardware. Oh, lost the presentation. Okay, this is a new technical difficulty. IT, can you give me a hand here? Okay. Okay, so rolling with the punches. Communication interfaces. So typically in building automation systems, we have BACnet and Modbus. And then MSTP is for BACnet, RTU for Modbus. For physical connections, we have Ethernet, RS-232 and RS-485 for that communication method physically. And then a little less common in commercial buildings is a wireless communication method, which is Wi-Fi. For data routing, it's important to consider, okay, are we storing the data locally, which is most oftentimes the case, or are we storing it remotely, cloud-based? Backup and internet outages are important to consider as well. What happens in that scenario, storage capacity, how long are we storing data, and then the frequency of data collection, maybe every 30 seconds, every minute, every day, every hour. It's important to consider that as well. And then software. The important part is, okay, it's not the most fun thing in the world to look at CSV files and spreadsheets, so we need some sort of data organization and analysis, some sort of graphical interpretation, reporting, and notifications from that raw data. We'll get into some key metrics to monitor now. On the ground loop side, mechanical equipment and district energy systems. So on the ground heat exchanger side, this is what a typical mechanical room looks like for a ground heat exchanger manifold. We have our manifold here, our supply and return lines coming up through the ground, and we have a nice flow meter here to measure the flow rate to and from our ground heat exchanger. We have temperature sensors here to measure our delta T, our supply and return temperatures, and with those two metrics, flow and delta T, we can get our energy, or BTUs. We also have pressure, right? If you have any leaks, that's important to analyze that pressure of the system. You can get that from flow rate if you have a catastrophic leak, but small leaks are good to catch with pressure sensors. On the mechanical equipment side, we can look at our kilowatt hour consumption of those circulation pumps. It can be a big portion of the COP, or the system coefficient of performance. Understanding the electrical energy of those heat pumps as well, maybe water to air heat pumps. In this case, if we understand our thermal energy and we know our electrical energy, we can get our COP, right? That ratio is our coefficient of performance. And then any sort of what people call thermal balancing equipment. to balance the loop field or backup equipment. How often is that backup equipment running? What efficiency is it running at? And how is that affecting our system COP? Because that's the whole point of these ground source heat pump systems, is you're supposed to be efficient. But if you're running backup equipment all the time, then that's not the case. New York State has put out a lot of technical metrics for their pilot projects. New York State has invested in pilot projects for district energy geothermal systems, and they want to look at a lot of data. And they want to look at every source and sink, so every ground heat exchanger module, whether that's open loop, closed loop. They want to understand the BTUs going in and out of that. They want to understand the customer side. How many BTUs is that customer pulling? They also want to understand the ambient loop pumps, the kilowatt hour consumption of those pumps, the backup equipment, whether that's a dry fluid cooler, a boiler, or any sort of, again, thermal balancing equipment, they call that. And then the heat pumps in the buildings. They want to understand the kilowatt hour consumption. Okay, so that's some basics on monitoring. Are we out of the woods? Well, not quite, because conventional monitoring systems have a few issues. One being scalability, two, fragmentation, and three, storage. In terms of scalability, the ground source heat pump industry only represents around 2% of the overall HVAC market right now. And what oftentimes we've seen, at least, is what we call the Wizard of Oz, the man behind the curtain. And what I mean by that is an engineer or somebody will pull the raw data. They'll get a spreadsheet or a CSV file, and they'll analyze it themselves, crunch the numbers themselves, put it into a report themselves. And frankly, that's not very scalable. And that's something that software could help them with. And if you have 100 buildings you have to do this with, that's something that could be automated. So current monitoring solutions aren't that scalable. Next is fragmentation. One of the learning objectives, I guess this is a little hint here, but one of the learning objectives is integrated versus fragmented systems, the difference. When you think of integrated systems, you can think of Apple, right? They have the iOS software, and then they have the Mac or the iPhone. Whereas a fragmented system, you can think of off-the-shelf components that are somewhat cobbled together. When you put together a monitoring system that's fragmented, you often have data accessibility issues. If you've ever experienced this, you'll know what I mean, but oftentimes when you use a fragmented solution, either the controls contractor will sort of hold the keys to the castle, and it'll be very difficult to obtain the data. And there's just a lot of finger pointing in terms of trying to collect that data. It's sometimes challenging. And so that leads to a designer performance feedback issue, right? Because you as the engineer can't get that data, or at least easily get that data. And since there's a fragmented, not a one-stop shop for your monitoring and performance, there's an accountability issue. Because oftentimes what we've seen is these building operators, they're doing their job, but they're somewhat misaligned with the person paying the energy bill, right? Because their job is to keep the lights on and make sure that building's comfortable. But maybe they're running the backup equipment more than they need to, and maybe that system COP isn't as strong as what was originally intended. Lastly is storage. Oftentimes, conventional systems only have around 2 months worth of storage, give or take. You can, specify a longer-term storage potential, but for ground source heat pump systems, we're more concerned with the month-to-month and the year-to-year in terms of the performance. So it's good to consider a longer-term storage capacity so that we can understand the performance optimization potential. And so no historical data hinders performance in terms of optimization. So what are some key features for monitoring systems then? Well, in our opinion, time-based insights across not only days and weeks, but months and years. We have intuitive interface for designers and building managers, and then actionable feedback tailored for those designers and engineers. Automated notifications and reporting. So again, this goes back to that scalability issue, right? If we have folks creating reports, those engineers could be spending their time maybe doing more interfacing with the customer and less number crunching. something that ideally provides actionable feedback and suggestions for efficiency improvements for these reports is also important to consider. And then some sort of notification that's generally distinct from the day-to-day operations and the minute-to-minute operations. The building automation system will handle that, but something that looks at the long-term performance and then the optimization potential of the system, not necessarily just keeping the lights on. And then lastly, building operator manual. This is probably the biggest thing that we've seen lacking. So what are some typical ground heat exchanger operating temperatures and flow rates that the designer has intended? What are the backup equipment set points and expected run times, right? How often should that building operator know to run that backup equipment? And then standard pump operation parameters for ground heat exchanger systems. So we're going to stop here and do a little checkpoint for Q&A before we jump into the case studies. So is there any questions?
If we have questions, we're going to bring you the mic so that you can state your name and who you're with. Okay, we'll get to everybody. Your name?
Rami Girgis from ME Engineering. So the problem of having a static model during the design, that is all what we can do. But how monitoring can help during the design phase? This monitoring system will be after the fact, after we have the geothermal well field in place. So is there any way to help with solving the issue of having a static model during the design?
Yeah, during the design, it's the best you got, right? Those are best practices. You do a detailed building energy model, and then you design your ground heat exchanger based on that. But again, there's a general problem with that because it's a static model. And okay, let's say you build a model for this room. What happens if they do a building or a lighting retrofit? What happens if they change the windows? That's going to change the heat loss. And the original design didn't intend for those changes. So yes, it's best practice to create these static models, and it's the best you can do. But then when you're commissioning the system, if you have a monitoring system that can change dynamically with how the system changes, that's, in our opinion, best practice as well. And that's what's missed in the industry a lot of times. And then as the engineer, you can take that information from the monitoring piece and that data to improve your practice. So let's say you have a multifamily building that you did a design for, and you're collecting data, and in a couple of years down the road, you have a very similar building down the street that you get a project for. Well, you can look at that data and then help inform your new design for that new building that's very similar. Good question.
Hi, Sarah Collado with Siemens. I missed the very beginning, and you might have covered this, but I'm curious about so the issues of data fragmentation and lack of storage ability, and that kind of plagues the whole building industry on the whole. And as many of you might imagine, as a controls company, it's something we've been looking at. So I'm wondering about the other side of the question is, how does some technology for GeoExchange report back up? Are you thinking towards a very open cloud-based platform where we can bring this into an even bigger data lake and start mapping like carbon emission across a portfolio of buildings and things like that?
Yeah, cloud-based, in our opinion, is sort of where it's going. And then that gives everyone access, right? There's no sort of closed walls.
And there's two pieces.
Well,
Sorry.
that's okay. No, good question.
The other pieces really are the data ontology of how things are structured and APIs to link things together.
Yep, for sure. Oh, good point. Thank you.
Hi, I'm John Dunn from Dandelion Energy. Do you see the importance of potentially creating a standard for protocol for what data gets transmitted to the cloud so that in this fragmented system we're all transmitting the same data? So it can be fragmented, but if we all comply to a certain standard?
Yeah, really good point. So it's early days. So I had the opportunity to be involved in the CSA 448 standard development, and that's a binational standard for ground source heat pump systems. And it's early days for monitoring. What we got in there is just a mandatory monitoring of temperatures. Folks thought that it was a burden in terms of costs. However, what we've seen is you can save a lot of costs on optimizing the size of the ground heat exchanger field, which is the most expensive part, right? Drilling those boreholes. So yeah, to answer your question, I agree, but we're not quite there yet in terms of the industry. But hopefully that'll come.
Any other questions at this time?
Yeah, we can keep rolling.
going.
Okay, so thank you for sticking through that. We'll get into some more fun stuff, in my opinion, which is these case studies. So we have a condo in Toronto. We have a seniors home in Northern Ontario, office in Winnipeg, apartments in Albany, and apartments in Corinth. So the condo in Toronto, 40 bores at 600 feet, water to air heat pumps in the suites, and a natural gas boiler for domestic hot water heating. Folks may have a little bit issue seeing this, but what we have on the upper graph is temperature, and we're monitoring our ground loop. So we have a BTU meter. So we have our delta T in terms of our temperature, so supply and return temperatures to and from our ground loop, and we have our flow rate on the lower graph. For the time frame, we're looking at October to December of last year. So anything sort of stand out to you folks for these graphs? Yeah, there's a pretty big drop here, right? Which is interesting because this is in Toronto, so November you're probably heating, and what happened was the controls contractor went to site for whatever reason, and this is a quote: "I switched the boiler to do the heating instead of the geothermal, so it will work better." So what happened here is not only did the building owner get a 70% efficiency drop right off the hop, right? Because they're switching from ground source heat pumps, which is a coefficient of performance of, 3 or 4, to a backup boiler, which is 80% efficient. So instantly tank their efficiency. And then second of all, in the summertime or springtime, they're handicapping their ground loop, right? Because they don't have as much capacity to work with in the summertime. So not only did they kill their efficiency in the wintertime, but they're also handicapping themselves in the summertime. So, and furthermore, nobody would have caught this if there wasn't monitoring, because first thing we thought, okay, is there any complaints in the building, right? When you see this sort of drop, you'd expect there to be comfort issues. People wouldn't be, warm or getting heated, but that wasn't the case. And so this would have gone on. Maybe the person paying the energy bills, the natural gas bill comes in the mail, they would have gone wide-eyed, but it's oftentimes things like this that happen that aren't caught and sort of accumulate issues. And so thankfully we were able to get the controls contractor to go back to site and turn back on the ground heat exchanger system to do majority of the heating. But again, that would have gone unnoticed all winter, and then they would have had issues in the summertime. Next is a seniors home in Northern Ontario. We have 32 bores at 500 feet deep, water source VRF heat pumps, and an electric boiler for backup heating. So this one, same graphs, right? We have our delta T on our ground loop, we have our flow rate. But one thing to note here is that we're in Ontario, so it's colder. The ground starts at around 46, 47 degrees Fahrenheit. So one red flag is, and for the folks who can't see, this is a week in December of this past year, right? So it should be heating. It should be pretty cold in Northern Ontario. So since our ground loop is only at around 47, that's a little bit of a red flag. And so we mentioned in the previous slide, they have the water source VRF units, the LG water source VRF units. And for those of you who've worked with those units, they have two modes. They have glycol mode and they have water mode. And what happened here was when the mechanical contractor was commissioning the system, they were having issues running the ground loop, because every time they turn on the ground loop and that water would go to the heat pumps, they would shut off because they're on water mode, which only allowed for 47, 46 degrees entering water temperature. And so what they did is they had that backup electric boiler, and they set the set point to 47 degrees Fahrenheit. Problem solved, right? Genius. And so these guys would have got killed on their energy bill. Not only are they paying for that electric boiler, right? But same problem. They have a limited capacity in the summertime because they're not drawing down their ground heat exchanger temperature. So what happened here is we saw this, and it stood out right away. And again, those VRF units, they have two modes, right? Water and glycol. When they switched the units to glycol mode, they were able to allow for entering water temperatures of 27 degrees Fahrenheit, which is for a geothermal application. They were able to lower that set point of that backup electric boiler to around that 28, 27 degree Fahrenheit mark. And then you saw this big decrease because the ground heat exchanger was actually allowed to do its job. And then it also fixed the cycling on the flow rate side because the pumps were allowed to operate more evenly as well. But again, only the person paying the energy bill probably would have caught this. The building operator, maybe they do care. I shouldn't be so hard on them, but at the end of the day, they're trying to keep the lights on. So there's a misaligned incentive with the person paying the energy bill, the original design engineer, and the building operator in most cases. So that was an interesting one. Next, we have an office in Winnipeg, vertical ground heat exchanger, water to air heat pumps, and electric baseboard heaters for backup. So same graphs, but we're looking at February to February, so around a year, February 24 to February 25. Another thing to note is it's cold in Winnipeg, so the ground loop starts at around 45 degrees Fahrenheit. And our ground loop, for those who can see, is around 60 in the wintertime. So that's a little bit of a red flag. And it's just sort of bouncing around, right? It doesn't look like it's being used. And then in the summertime, we have a nice delta T. Nice cooling. This makes a lot of sense. Have an increasing ground heat exchanger temperature. And in the wintertime, again, we have some issues. So what happened on this one is each office had baseboard heaters, and they were manually controlled. And people would come in the wintertime and just crank their baseboard heaters in their office. And the ground source heat pump system, the water to air ground source heat pumps were on a separate thermostat, completely independent systems. The thermostat were in the hallways. And so those backup baseboard heaters are supposed to be backup, were heating and triggering that thermostat for the geothermal system to do cooling. So the systems were fighting each other. And this went on for 10 years. We got involved in this one 10 years after the fact. And people were complaining about comfort issues and high energy bills. And thankfully we caught it thanks to monitoring. But again, it's things like these that happen in the wild that don't necessarily get caught unless you're looking at the data. And then you can see in these graphs here, so we have monthly energy loads. The blue represents cooling. So in January, February, we have a lot of cooling on our ground loop, which doesn't make sense in a colder climate. But in summertime, it's fine, right? Because there were no backup equipment for the people to run in the summertime, so they had to use the GeoLoop. So next we have an apartment in Albany. We have 32 bores at 500 feet, water to air heat pumps in the suites, and a CO2 heat pump for domestic hot water heating. So important to note here is it's 100% geo, which is pretty cool. Same graphs, right? This is a year of data, and they look pretty good, right? You get your typical sine wave of your geothermal system, but one thing that stands out here is when you think of your ground heat exchanger design, your typical goalposts for temperature, for your design temperatures are 90 on the upper end-ish, down to 35 or 40 degrees Fahrenheit in the wintertime. So those are sort of your goalposts. And the green line here represents the ground heat exchanger temperature. So we're only getting up to around 70 in the summertime, which is, a little bit, it's fine, but it's a little bit under what's expected. And then in the winter time, we're only getting down to 45, 50. So what we see here is that, okay, maybe the customer overpaid a little bit for their ground loop, and maybe it's a little oversized. But that's okay, because if there's another system that's similar to this project, or if the engineer gets a similar project, they know that they can right-size the system, right? They can maybe they overdid it a little bit, maybe it was one of their first ones, and now they have the information to right-size in the future because they're monitoring. And on top of that, we talked about the difference between the static model for the original building energy model, and then oftentimes it's different than the energy loads that the building sees. Well, now that we're monitoring, we can compare that original building energy model with the actual loads that the building is seeing and see how we did on the design side and use that feedback for future projects as well that engineers can use. And then furthermore, your favorite ground heat exchanger sizing software uses algorithms to calculate the future design temperature of that ground loop. And I'll give you a little insider hint, those models are wrong, right? But it's a question of how off they are. They're generally conservative, but they're theoretical models. So as you collect more and more data, you can improve those theoretical models into empirical models based on that specific site and that specific building. So as an engineer, you can furthermore improve your practice by utilizing this. And then last one here, we have an apartment in Corinth, 28 bores at 500 feet, water-to-air heat pumps in the suites, and CO2 heat pump for domestic hot water heating. So another 100% GEO one, pretty cool. A week in February, we're looking at this past year, February 2025, and looks okay, right? The only thing that they could possibly tweak to improve performance is reduce the flow rate to achieve around a 4 to 5 degree delta T in the wintertime. And what this would do is help that building owner pay a little bit less on pumping energy. And so that is all I got for the case studies. We got to run through these learning objectives. So hopefully I did a good enough job and we can answer these questions. So first question is, what are the two types of sensors needed to measure BTUs? I'll give you a hint. We just looked at a bunch of graphs with them.
We know.
Yeah, so temperature sensor and flow meter. Can we name one communication protocol? Looking for building automation systems. There's two main ones. Yeah, BACnet and Modbus. What is the difference between a fragmented and integrated system? We touched on this a little bit. You can think of Apple maybe versus PC. Yeah, this is a longer answer, so you can't really blurt it out. But fragmented systems have multiple components that don't talk to each other easily. And then can you name one key feature of a monitoring system? Yeah, so I put building operator manual there because that's, in our opinion, most important. But yeah, great. So thank you for hanging in there. I'll stick around for any questions, but you've been great. So thank you guys.
Plenty of time for questions. We'll be able to get to everybody. Your name.
Hi, I'm Aaron from SUNY. Your first scenario there where the guys turned on the boilers and shut off the heat pumps, why?
Well,
Because some of us, the operators that are in the field, we have to respond to immediate complaints immediately.
Yep.
So oftentimes we do drastic things like that.
Yeah.
Not me, of course. But I just wanted to know why. Was he doing his job or was he doing something wrong?
Yeah. So
Sorry.
there's and great question. There's been a couple of misconceptions in the industry. One, these systems are really expensive, and two, these systems don't work. So what we've seen a lot of times is controls contractors or building operators have a general bias to not believing that these systems won't work. And then they don't want a phone call, right? In January, they don't want to have to go to site. And if their contract's up for the project, that's out of their pocket that they have to go back to site, or maybe they charge the customer and they don't have to do that. So what we think the reason why is because they just didn't want to get a phone call, right? They changed the system to run the boiler that they knew would work all winter. They probably didn't think that geothermal would work all winter, and so this was the solution. Yeah.
It's,
I got it.
Same question from. Go ahead.
Will it work now? Okay, good. We were asked to come in and take a look at a hotel geothermal system that had been running for about 5 years. Just the owner just wanted to know how it was operating, and because he had no clue. And I guess the first thing we noticed that it was in January, and the loop temperature was 60 degrees, and then we found there was a boiler on the system, and the sequence was completely screwed up, and it was trying to maintain 60 degree, loop temperature. But we work with the controls contractor to write a sequence, that would let the backup just do backup. But it's not that easy to figure out a good sequence that doesn't start warming the ground, and they don't believe that the controls contractors really don't believe it, that you just want it to bring the temperature up a tiny bit, and let it go back. But that's a problem, figuring out a good sequence that's going to not waste energy with the backup boiler on any system.
Yeah, I agree. You're preaching to the choir here. I guess the solution may be, when you're originally designing the system, you have to think things through. And so it sounds like after the fact, maybe the system wasn't configured in a way in terms of the piping to make it easily allowable for that backup equipment to do its job, which is being a backup portion rather than the primary portion. So yeah, it's good to get in front of things and sort of try and be preventative and perform good design practice. But if the system isn't configured in the correct way or piped in the right way, there's not much they could do in that scenario, right? So monitoring is important for sure, but so is good design practice.
Thanks for the talk. For the predictive modeling and optimization, is the way that people are going tuning the parameters of the theoretical model, the physics-based model, or is it just going purely empirical based on the data?
Yeah, both. I can't speak for other people, but what we're looking at doing is tuning that theoretical model based on the empirical data.
One of the reasons I'm in the room, Sarah Collada with Siemens, is because we offer performance guarantees on our projects. And I'm wondering if you would suggest any key performance indicators that, this kind of data would report out on, or could even, alarm that we're not hitting those KPIs. I'm not an engineer, so you'd have to translate it into layperson's terms for me.
Yeah, great question. So from what we've seen, it's not very feasible to measure the system COP, especially in a commercial application, right? You got to monitor every pump. If there's a ton of water to air heat pumps, you got to measure every one of those with electrical monitors, and then understand the thermal energy to get your total electrical energy as the ratio to that thermal energy. So not very feasible. But from what we've seen, which is pretty feasible, is you can put a BTU meter on that ground loop. And if you know that you're maximizing the use of that ground loop, you're just about at peak efficiency, right? Because you're utilizing that source as much as it could be utilized. And so I don't know how your contracts are written, but yeah, if you're offering, a certain amount of guaranteed savings, you'd probably want to measure and verify that, but it can be costly. If you have a central plant, maybe a little bit less costly, but in a lot of cases, there's water to air heat pumps throughout the building, maybe in each suite. For a multifamily building, that is very, very not so much cost effective. So yeah, to look at that ground loop, understand, is it maximized in terms of its usage, then you're probably 80%, 90% of the way there.
Oops, sorry.
I'm Jim Snyder, and I'm just a simple geothermal installer, right? But we went to this school, and of course, I'll use some names. So one company was trained, put in the things. Another company did the design. Honeywell does the energy management, and it's fragmented, right? You know, they asked me to come and look at a couple of things. The interesting thing, I think, why this is so important is that these guys are blowing up these machines, these heat pumps. There's not enough flow going through the units and those types of things. But I guess my one question I have is the frequency of data collection. What is it every minute? Is it every hour? Maybe you could help with that a little bit.
Yeah, great question. I'll give a typical engineer's answer. It depends. But for performance on the ground loop side, we like 30 seconds. And it depends your setup too. If you have, because you got to pay for storage capacity, right? We pay a premium, but we offer a lot of storage, lifetime storage at 30 seconds for the lifetime. So, yeah, I guess going back to your original question, if you went into that school and you had to say, okay, guys, we got to look at a certain frequency of data collection, probably every hour or 10 minutes you'd be able to diagnose the issue. You'd be able to figure out what's going on there, and then not, kill your server racks from storing a ton of data.
Okay, we'll take one more question, and then I just want to remind people, if you're here for the credits or the professional development hours, you have to find your name either on the printed page and just sign next to it, or if you haven't pre-registered, there's blank sheets. We need your information. There's 4 different pages. You only need to do it once. There's a couple duplicates, so I didn't want everybody to stand in line for one page. Hope they make sense. So where was the question here?
So for cloud-based storage, we normally have an issue with a lot of facilities about cybersecurity and trying to get any information out of their environment. So how are you guys handling this and when you have these challenges?
Yeah, so we've worked with banks before. Banks are, probably the most cyber secure, and you just need to get in early on the project. If they're buying in on the process and buying in that this is important, they'll create firewalls and they'll create porting that allows you to get to the cloud. But if you're coming in after the fact, whether it's the sunk cost fallacy or human stubbornness, it's challenging to convince people to change what they're doing, but it's easier to get in at the very beginning.
Okay, so next session starts in about 15-20 minutes. Can I get a round of applause for Connor? And Connor, are you going to be around for questions if people have individual? Okay.
Yeah.
Thank you very much, everyone.
Thank you.